One product came back in stock. 40,000 people had asked to be told about it. By the time the on-call engineer killed the job, some of those people had been notified 11 times, and the email provider had started rejecting everything the company sent for the rest of the day. Nobody wrote a bug that morning. A retry, a queue, and a for loop combined into something none of them was on its own. So let's look at how notification systems actually break, and the design that keeps a fan out from turning into a flood. The obvious design is a loop. An event arrives, you load everyone who subscribed to it, and you send them each a message. It works perfectly in testing, because in testing the list has 4 people in it. The problem shows up at 40,000, and it is not speed. It is that the whole fan-out is a single unit of work. Halfway through, the process is redeployed, or the provider times out, or the job runs past its limit, and the scheduler kills it. Whatever the reason, the job restarts, and because the only thing the system recorded was whether the job finished, it starts again from the top. The first 30,000 people who were notified correctly get told a second time. Run that loop 3 times and you have the 11 notification morning. The unit of work is wrong. Delivery to one person succeeded or failed, but the system only tracked whether all 40,000 did. So make the unit of work match the thing that can independently fail. Split the fan-out into 2 stages. The first stage does nothing but expand. It takes the event, reads the subscriber list, and writes 1 message per recipient onto a queue. That is all it does, and it is cheap because it never talks to the email provider. The second stage is a pool of workers, each pulling 1 message and delivering to exactly 1 person. Now, a failure is small. If a delivery fails, that 1 message goes back on the queue and gets retried on its own, and the other 39,999 are untouched. There is a related decision worth naming. You can expand the audience at write time, the way we just did, or expand at read time, when each person opens their inbox. Write time fan-out costs storage and makes the read instant. Read time fan-out costs nothing until someone looks, but the read gets expensive. For notifications, you almost always expand on write, because the whole point is to reach someone who's not currently looking. Splitting the work fixes restarts and introduces a new problem. Queues deliver at least once. A worker can deliver the email, then die before acknowledging the message, and the queue will hand that same message to another worker. So the consumer has to be idempotent, and that means a DID-up key, the event identifier, the recipient, and the channel together. Before sending, the worker claims that key. If the claim fails, someone already sent it, and the worker acknowledges and moves on. The second problem is the provider. It is a shared resource you do not own, with its own limits, and 40,000 messages arriving in 10 seconds looks exactly like abuse. That is why the whole company's mail stopped that morning. So you put a rate limiter in front of the provider, sized to what it will actually accept, and you let the queue hold the backlog. That is what back pressure buys you. The spike becomes a slightly longer delivery window instead of an outage. The finished shape has 5 parts. An event lands on a topic. An expander turns it into 1 message per recipient. A pool of workers delivers them, each claiming a DID-up key first. A rate limiter sits between the workers and the provider, so you never send faster than it will accept. And anything that fails repeatedly goes to a dead letter queue rather than retrying forever, because a message that has failed 20 times is not going to succeed on the 21st. Notice what this design gives up. It does not promise exactly once delivery, because nothing does across a network boundary. It promises at least once delivery with an idempotent consumer. which is the same outcome and is actually achievable. Every part of that pipeline has a name, and the names are older than most of the tools we use to build it: splitter, idempotent receiver, dead letter channel, competing consumers. If you want the full vocabulary and the cases where each one is the wrong choice, the Enterprise Integration Pattern series works through them properly. That is where to go next.